Hi, my name is Ishan, and in today's video we're going to be talking about nuclear thermal propulsion. Nuclear thermal propulsion. It sounds pretty sci-fi, doesn't it? Spaceflight is having a resurgence nowadays, with companies like Elon Musk's SpaceX promising rides to the moon and Mars. But at a certain point, conventional rockets simply don't cut it for sending super large and heavy payloads to the moon and Mars. So the rocket equation tells us that at a certain point, liquid-fueled engines simply do not have the performance for sending high volume and very heavy payloads into deep space. Nuclear thermal propulsion can enable a future where humans can travel efficiently and quickly into the depths of the solar system, settling Mars and mining asteroids. Let's get into it. To understand how nuclear thermal propulsion works, it's important to understand how a regular rocket engine works. The recipe for a normal liquid-fueled rocket engine is a fuel plus an oxidizer plus some source of ignition equals lots of fire, lots of energy, and a giant structure shooting up into space. In fact, a liquid-fueled rocket engine uses the same combustion principles as your average car engine, except because there is no oxygen in space, they need to carry it with them to use as an oxidizer for the explosion in the rocket engine. When a rocket engine starts, pumps push the fuel and oxidizer into a combustion chamber, where they are ignited. Once combustion is occurring, the cycle is continuous, and as more propellant is pumped into the combustion chamber, it continues to explode. The high-energy gas formed by this explosion is directed by a rocket engine's nozzle. The nozzle uses an ingenious converging-diverging hourglass shape, which uses the properties of fluid dynamics to accelerate the gas to supersonic speeds. The reason this is important is because a rocket engine's performance is directly related to how fast the gas is moving, i.e., you want the gas to be moving as fast as possible to maximize the thrust and performance of the engine. Okay, now that we understand how a liquid-fueled rocket engine works at a high level, let's get into the workings of a nuclear thermal engine. The concept for a nuclear thermal engine was originally drawn up in the 50s, with NASA even conducting ground tests in the 60s and 70s, accumulating over 2 hours of runtime. However, in 1972, the program was canceled for NASA to focus more on the development of the space shuttle. There are two main differences between an NTP engine and a liquid-fueled one. The first being that an NTP only uses liquid hydrogen as its fuel. The second being the presence of a small nuclear reactor instead of the combustion chamber. If you remember back to when I was talking about liquid-fueled rocket engines, keep in mind that a rocket's thrust is produced by the high speed of the exhaust gas. In a liquid-fueled rocket, combustion changes the fuel and oxidizer into that high-energy gas. So how does this process happen in a nuclear system? In an NTP rocket, fission inside the small nuclear reactor, fueled by uranium-235, creates a large amount of heat. Fuel pumps pump the liquid hydrogen around the reactor core, heating it up. At a certain point, there's so much heat that the liquid hydrogen turns into a gas. At this point in time, it's still being heated up, adding energy, so by the time it reaches the nozzle after being flowed around the reactor core, it's a high-energy gas, similar to the gas produced by combustion. At this point, the engine uses the same nozzle design of converging-diverging hourglass shape to accelerate the gas further to the supersonic speeds required for the rocket to function. Moving on, let's take a closer look at how nuclear thermal propulsion can enable that future state I was talking about. Simply, it all comes down to efficiency. NTPs can burn for longer using less propellant than other engines, making long-distance trips shorter and more economical. In addition, the fact that the rocket has to carry less fuel means it can carry more stuff like people, cargo, and supplies. Nuclear thermal propulsion systems will also cut down the travel time to Mars by 25%, and additionally, you won't actually have to wait for a Mars transfer window, which comes every 16 months. In addition, nuclear thermal propulsion engines are doubly as efficient as the most efficient rocket engines ever flown, the RS-25 Space Shuttle main engines. Wrapping things up, nuclear thermal propulsion can enable a future where humanity is exploring out amongst the stars in a faster, more efficient, and cost-effective manner than ever before. Entire new industries will open up, such as asteroid mining, and larger, more complicated deep space scientific missions, enabling us to learn more about our solar system. In addition, NTPs would allow faster travel between the Moon and Mars and allow for the large volume payloads needed to settle Mars to be carried there. Thanks for watching.